All right, so we said at the beginning of the semester that there were going to be 5 mathematical processes with vectors that we were going to have to become comfortable with. So adding vectors, subtracting vectors, multiplying a vector by a scalar, multiplying 2 vectors together in a way that gives back a scalar, so that's the dot product. And then the 5th of these is what we're dealing with now, which is multiplying 2 vectors together that gives back a vector. That's called the cross product. And so the cross product, which is also known as the vector product, that's our way for multiplying 2 vectors together that gives you back a vector, which means that there's got to be both a magnitude and a direction in our answer. So algebraically, there's a rule, and we'll start with using sort of the simplified version for 2-dimensional vectors because that's most of what we'll deal with. And basically it says if you can break up 2 vectors A and B into their x and y components within some particular coordinate system, then the cross product A cross B is the product of the x component of vector A and the y component of vector B minus the y component of vector A times the x component of vector B. So literally what you're doing, right, you can think of, I'm taking my 2 vectors, I'm breaking them up, here's the x components, here are the y components, and the cross product, algebraically, our rule is given by multiplying together along that angle, so ax times by, and then I want to subtract, and then I multiply together on that angle. So you can see sort of the symbol we use here of the x is kind of helping denote where that algebraic rule comes from. So in 3 dimensions, so now I've got x components, y components, and z components, you'll notice that this ends up with a more complicated expression. So when we just had a 2-dimensional vector, this is what we had. We had ax by minus ay bx just in the z direction. And again, whether that points in the positive z or negative z is entirely a function of whether this product is larger or smaller than this one. So if this product is greater than that one, then obviously your cross product will point in the positive x direction. If this product, if ay bx, that product is larger than this one, then again it'll point in the negative z direction. But when we have 3-dimensional vectors, basically we just have sort of 3 rules. So we've put this together for each dimension, and so this gives us a aybz minus azby. That will tell you what's going on in the x direction. So notice that the x component of your cross product involves the other 2 components, the y and z components of your original vectors. The y component of your cross product involves the x and z components of your original vectors. And the z component of your cross product, that's the x and y components. So this is just sort of our rule. Fundamentally, one of the things to make sure we understand about cross products is the cross product of 2 vectors is perpendicular to the plane defined by both vectors. So in the same way that we would say that you can define a line with 2 points, you can define a plane with 2 vectors. So as long as you have 2 vectors that aren't collinear, they don't lie along the same line, those 2 vectors define a plane. And the cross product of those 2 vectors will always be perpendicular to that plane. So one of the things that we'll emphasize here is that the cross product will be perpendicular to both vector A and vector B. So we'll take advantage of this, the fact that the cross product is going to be perpendicular to the plane defined by our vectors. We'll take advantage of that in working some of the problems that will deal with cross products. Now, if I want to think about the magnitude of the cross product, well, it works out that I can calculate the magnitude of the cross product by thinking about the magnitude of vector A times the magnitude of vector B times the sine of the angle phi, where the angle phi is again defined to be the angle between vectors A and B. So I can think about this sort of in 2 ways. One is I can kind of rearrange and put the B sine phi term together as a single piece. And again, if I think about b sine phi, well, if this is my angle phi, sine phi would be this perpendicular component of the vector b. So one way to think about the magnitude of the cross product is it says take the magnitude of A times the magnitude of the component of B that is perpendicular to A. Now obviously I can flip the sine phi term around and pair it with A rather than pairing it with B. And so again, that would be thinking about, well, this breaking up vector A into a parallel and perpendicular component. And again, given my angle phi, A sine phi would be the perpendicular component of vector A to the line of vector B. So I can, in either way, whether I sort of choose to pair the sine phi with the B, the magnitude of B, or pair it with the magnitude of A, I notice that largely what it's telling me about is basically how much these two vectors are perpendicular to each other. So the larger this perpendicular component is, in either case, the larger the magnitude of the cross product is going to be. Now, with this in mind, I can come back and think about that think about the cross product in terms of a geometric rule. So again, here's my vector A, vector B. They form some plane. And again, given the fact that I've drawn the cross product A cross B is basically pointing up, this tells me that A and B have to both lie within a horizontal plane. That's the only way that I can get their cross product to be perpendicular and point upwards. And so the things that I take out of this are A, is that the direction of the cross product is, again, it's perpendicular to the plane defined by both vectors. It means that A cross B is perpendicular to vector A and is perpendicular to vector B. But in terms of magnitude, I said that's how I calculate the magnitude of the cross product. And oddly enough, it works out that that magnitude basically is saying if you complete the parallelogram that's basically started by your two vectors, the area of this parallelogram happens to be AB times sine phi, where phi is defined as that angle between the two of them. So this means that the magnitude of our cross product is equal to the area of the parallelogram defined by the vectors A and B. So this is our geometric rule about a cross product, that its direction is perpendicular to the plane that those two vectors sit in, and its area is equal to the parallelogram created by those two vectors. There are a couple of special cases that are worth talking about. So obviously, if A and B are collinear, well, they can be collinear and both point in the same direction. In that case, phi would be 0. Sine of 0 is 0. Again, this tells me that the A cross B, their cross product, is going to have a magnitude of 0. Another way to think about this is, if they both lie along the same line, they don't carve out a parallelogram at all. So geometrically, there's no angle there to deal with. When they're perpendicular to each other, so when vectors A and B are perpendicular to each other, that's going to be a situation where now I have the sine of 90 degrees. Sine of 90 degrees is just 1. And I'll end up with that the magnitude of A cross B is just equal to the magnitude of A times the magnitude of B. And again, I notice that means that the cross product is at a maximum when my two vectors are perpendicular. So I get smallest magnitude when they lie along the same line, largest magnitude when they're perpendicular to each other, because again, what the cross product is trying to tell me about is how much two vectors are perpendicular to each other. Obviously, I can have two vectors that are collinear, but instead of pointing in the same direction, they point in opposite directions. All that does is say that instead of phi being 0, phi is 180 degrees. But the magnitude, in that case, is still 0, because both these vectors lie along the same line. Now, one of the things to emphasize here is if instead of lying along the same line, let's say vector B pointed up at some angle, well, there would really be two options for how I could define phi. We're always going to pick phi to be the shorter way around. So I could go all the way around so that I had phi larger than 180 degrees, but that's never the choice that we're going to make. So the sine of any angle up to 100 degrees is never negative. And since we want to calculate the magnitude by magnitude of a vector times magnitude of a vector, we know both of those things are positive, times sine of an angle. In order for that magnitude to always be positive like it needs to be, that means our angles can't be larger than 180 degrees. So we're always going to define the vector phi to be the quickest way around the angle between the two vectors that is less than 180 degrees.